Hello, welcome to this lecture on environmental impact assessment of airport development, which is part of the course on air transportation. Airports, as you know, are quite large in size, and whenever an airport is either constructed or if it is extended or developed, there is going to be a huge environmental impact of this activity, and today we will look at how this impact is assessed. So first we need to learn to differentiate between environmental assessment and environmental impact assessment. Environmental assessment essentially means it depends on the location of the airport, it depends on whether you are building a new runway in a non-metro area. Is it involving a major runway extension? Then there could be runway strengthening, and that would lead to a larger and noisier aircraft to operate from there. There could be an expansion of the terminal and the parking, which could be major, or there could be installation or relocation of the instrument landing system, one of the primary navigational aids required for landing of the aircraft safely. There could be a requirement to acquire land for various purposes, both the airside area and the landside area. And for that, we have to look at facility modification, we have to look at relocation of businesses and residences which are there on the land occupied near the airport or in the area where the airport is to be developed. We may end up affecting some historical sites or archaeological sites, and there are restrictions on that. And it could also affect the floodplains, the wetlands, the coastal zones. All of these are very important. Environmental impact assessment essentially relates to adopting a new airport system plan, so where the substantially different criteria are there from the existing criteria. There are greenfield airports or airports which are developed afresh in a new area, such as the Navi Mumbai International Airport being developed in Navi Mumbai. Then you could also look at new runways in metro areas, as we have seen earlier. Now there are three major pollution factors or PFs. The air pollution because of the operation of the aircraft, water pollution because of the creation of the airport and also because aircraft need to be regularly cleaned, and also noise pollution. When you fly an aircraft in the vicinity of the community, there can be a lot of noise which can lead to many ill effects on the population living around the airport or near the airport. So we will look at all of them today. Let us start with air pollution. The general public feels that the climate impact of air travel is just the creation of the CO2, but that is not true. More than CO2, there are a large number of other pollutants produced, such as the nitrous gases, the soot particles, sulfate, water vapor, etc. And all of these affect the formation of ozone. The climate impact can be direct or indirect. Okay? And the contribution to the global warming in proportion to CO2 can be of the order of around 2%. So it is a large percentage. Even the creation of those contrails which you see behind the aircraft, or creation of cirrostratus clouds of ice which can affect the atmospheric properties. So aircraft emit many things apart from CO2. The aircraft emit the various nitrites of nitrogen, so NOx, carbon monoxide, hydrocarbons, many particulates and sulfates. Now 24,000 commercial jet aircraft were operating approximately in the year 2020, and this number is constantly increasing over the times. Now in 2019 we have the data that the flights all over the world produced 915 million tons of carbon dioxide, which, as I mentioned in the previous slide, approximates to about 2% of all human induced CO2 emissions. This number is also increasing. 43 gigatons of CO2 is expected to be produced by 2050. 43 gigatons, right? Now, the thing is that when you have NOx emissions and when you combine it with air, you get ozone, and that increases the effect of global warming. The aviation emissions have increased 95% between 1990 and 2016, primarily because of the increased number of passengers and also large number of aircraft. So, you can assume that they have roughly doubled from 1990 to 16, and they may quadruple in the next 10 years, that is the estimate. The NOx emissions have also gone up by 55% from 1990 to 2016. So, the pollution levels are increasing day by day, and the good news is that the hydrocarbon and the carbon monoxide and particulate emissions are relatively same. This is because of the design and improvement of the jet engines. Now, water vapor plus oxygen creates these clouds or contrails. These are called as contrail induced cirrus clouds, and these are going to trap the infrared rays, and it will create a global warming effect which is 3 times that created by only the carbon dioxide production. Plus there are soot particles emitted, and these soot particles, they act as the nuclei for condensation of the water vapor, and that forms clouds and it forms rain. Okay. So, that is why it is not really a good idea. A picture here shows the creation of the contrail induced cirrus clouds when aircraft are flying. One author looked at contribution by that individual's practices over the year. So, he says that 2/3 of the annual emissions are because of the flights. Okay? That means 13,500 kilograms of CO2 was emitted because this author has travelled 50,000 miles. In comparison to that, the carbon dioxide equivalent produced by electricity usage, by natural gas usage for cooking, by sewage, food and cars is far less. So, in 2010, this particular author said that I have emitted 19,000 kilograms of CO2 equivalent. Okay. So, it is a large, so especially those who are frequent flyers and travel extensively on leisure or business, they contribute a lot to the pollution. Now, the typical pollutants near the airport are carbon monoxide, hydrocarbons, nitrogen oxides, sulfur dioxide, suspended particles and the photochemical oxidants. All of these are very harmful and they can lead to detrimental health effects of the people residing near the airport. All of this contribute to the percentage. Now, the procedure for air quality assessment involves these particular steps. You first look at the travel demand, first of all directly by the aircraft and also with the access vehicles, the taxis that you take to report to the airport, and then from the destination airport to the location where you want to go. Then you look at service vehicles that are required at the airport to service, their numbers, their types, their mix, all of that along with the airport configurations. It gives you the flow rates and speeds. Then there are other vehicle characteristics, then you get the emissions. Emissions can be then looked at how they affect the met conditions, the ambient conditions and the diffusing chemical reactions. All of these together affect the air quality and that impacts the plant life, the animal life and the health. Moving now to water pollution. This is an example from Kansai airport where they have tried to clean the water that is supplied. So, they are treating the waste water, okay. 865,000 cubic meter of water has been treated. Out of that 572,000 is reclaimed back to this airport and that is used for multiple things like toilet flushing, watering the plants, cleaning of road and tarmacs, okay. Plus there is the clean water supplied and the remaining is discharged to the Osaka Bay. So, this is a snapshot of the groundwater processing plant that is operating at Kansai airport, okay. And you can see how clean the water is when it comes out from the treatment plant. De-icing of an aircraft to handle it operating during the winters can also create a lot of pollution, because these chemicals which are sprayed to the aircraft, they have to be washed away, they have to be cleaned, and that requires a lot of drainage. So there was a study done in 2010, the environmental impacts of airport de-icing on the water quality. This study concluded that apart from polluting the airport, the de-icing fluid discharges have been known to affect drinking water treatment process and the quality of finished drinking water. Okay? And therefore, it is not just direct pollution, it is also indirectly adding to the pollutions. Now let us go to the noise. What is noise? Basically, noise is undesirable sound which causes irritation, and therefore it becomes undesirable, nobody wants it, it causes a lot of problems. There are many issues which come up because of noise pollution. First of all, an aircraft jet engine is inherently very noisy, very noisy. Noise level is measured, noise is a pressure wave, so its level is measured in decibels. Okay. Now during takeoff with full throttle, a typical jet engine could generate noise as high as 140 decibels, which can be very deafening and loud sound. Okay. During cruising and landing, the sound level becomes nearly half. Now prolonged exposure to more than 90 decibels can cause permanent hearing loss. Now in the European Union, approximately 1 million people are living near the airports, and they are exposed to more than 50 aircraft operating on an average with noise levels more than 70 decibels per day. This was a study carried out in 2017. And as the years progress, this number actually keeps increasing. This number is 60% more than that corresponding number in 2005. So it shows at what rate it is growing. Managing aircraft noise is a huge issue. Now noise can induce hearing loss in the individual, because the sound waves will travel to the inner ear, and loud noises can cause issues in the cochlear duct, and it can create damage to the system. And the frequency in kilohertz is very much important when you look at the effect on the human ear. Now if you look at community annoyance because of noise, percentage of people that are highly annoyed as a function of the day and night average sound level is on the y-axis, and the x-axis goes on the noise level in decibels. So when it is around 50 to 60 decibels, there isn't much problem, only about 8 to 10% people are affected. But when the noise level rises to 80-90 decibels, almost all who are living nearby are annoyed. So what are the annoying effects of noise? There are 3 levels or 4 levels. There are auditory effects, it causes fatigue and partial or complete deafness. Then there could be extra auditory effects, which is annoyance, fatigue, lack of concentration. There could be biological effects like sleep disturbances, autonomic functions like cardiovascular, endocrine and digestive can be affected. Plus it can also affect the growth and immune system. And finally there are behavioral effects. Medication intake may increase, psychiatric symptoms may also increase, and there could be impact on learning. All of these together, all these 4 are the auditory and extraordinary effects of noise. So it's a huge pain point. So therefore, the regulatory bodies are first interested in quantifying the disturbance because of noise, and then they impose restrictions on the amount of disturbance that can be created by the aviation. So noise measures. So the first and the basic measure of noise is the decibels with A-weighted adjustments, okay, because each frequency of the sound and each pitch of the sound does not create the same level of disturbance. So there is a weighting proportional to the frequencies and pitch of noise, that is the dBA. So human ear is very sensitive in the range of 2 to 4 kilohertz. If you have sound in this particular range, it is much more painful and disturbing. So we add 2 or 3 decibels for sounds in the highly sensitive range of 2 to 4 kilohertz. Then there are single event measures of noise. whether noise is continuous or whether it is in one big shot or one big spike, it also makes a big difference. So, the single event noise basically is noise due to one aircraft movement which is spread over about 10 to 20 seconds, after which it goes far away, so you do not hear it. So, Lmax stands for the maximum sound level recorded in time to interval t, and SEL or the sound exposure level is the total noise impact in time t. Then you have also cumulative measures of noise, because if you are exposed to noise continuously for a long time, it all adds up and creates a bigger nuisance. So, the total noise effect of all movements during the time interval t at a place is called as a cumulative measure of noise, and it could be measured in terms of equivalent noise level or day and night average sound level. So, LEQ and LDN. Here is how the distance from the noise source affects the communication. So, the relaxed conversation where the sentence is intelligible is 100%, that can vary linearly from around 58 to around 20 decibels as you go far away. Okay. But when you have the very large value, you have to speak very loudly, and that means when the noise levels is from 80-82 decibels right up to about 65 to 60 decibels when you are proceeding at 20 meters from the source. Okay. So, to quantify the disturbance because of noise, we have some airport certification. So, the LDN, day and night average 65 decibel noise contours near airport are plotted. Then there is a community noise equivalent level. So, this is a weighted average gathered over 24-hour period, and there are different weights for day, evening and night noise, with the highest penalty or highest weight for the night, less for the evening and least for the daytime. So, in airport certification, we use the LDN 65 noise contours and CNEL, but when we certify the aircraft, we look at the perceived noise level in decibels, which takes care of the subjective effects of loudness and annoyance. Okay. This is a weighting based on the sound pressure level. So, if you look at EP and dB, then you have effective perceived noise level in decibels, where the effect of duration also is increased. So, when you certify the airport, you look at CNEL or LDN. When you look at aircraft certification, you look at PNDB or preferably EPNDB. Okay. EPNDB also caters for spikes in the frequency spectrum and all the tones that you hear. Have a look at the assessment of noise pollution. LDEN is the average SPL for day and night, day, evening and night. Okay. It is an average sound pressure level per year. Then, as I said, there will be a penalty for the evening, 10 for the night, and then you have L night, which is the average sound pressure level per year for the night period only. A study was done at 47 major UU airports, and it was found that around 2.5 million people live inside the contour of LDEN 55 decibels. 55 decibels is almost the threshold of getting disturbed because of the noise, that is where it starts, and nearly 1 million people live inside the sound level of 50 dB. So, this is how SPLs are measured, basically sound pressure and sound power. Okay. So, sound power is a logarithmic function which has got a weight of W upon W0, and similarly the pressure also is in terms of measured in terms of decibels. Let us have a look at now, the threshold of hearing is around 5 decibels, then broadcast and broadcast studio will be operating at 15 decibels. At a night or a bedroom in a concert hall would be around 30 decibels. This is the quiet rural night time, and then slowly if you increase, when you look at a rock band or when you look at a Concorde landing 1000 meters from the runway end, you experience 110 decibels. Okay. So, you can compare now, a vacuum cleaner at 10 feet is around 70 decibels, and the same thing is 757 from the start of the takeoff. So, on the left hand side, we have given some idea about the aviation related noise and the urban and the rural noise level. On the right hand side, we have given the comparable values from other sources. Here is a graph that talks about the various noise levels and the gains. Here is a graph for maximum A weighted sound level typical aviated sound level time history of the aircraft as it passes by, you can see that as it goes by, the sound level increases from 50 to about 85 and then comes down to around 50 again. Sound exposure level SEL is an important parameter. This is the total sound energy contained in an A-weighted constraint in the noise level. This is measured using a logarithmic equation, where the LAE is the sound exposure level, T0 is 1 second to maintain a dimensionless argument for the logarithm, LAT is the continuous A-weighted sound level function, and note the limits of the time from t equal to 0 to t equal to t are sufficient to encompass the top 10 to 20 dB of the noise events. Let us see how we estimate the SELs. Here is an example. So, suppose the following sample of A-weighted sound levels was measured at 0.5 second intervals during an aircraft flyover, 64.5, 66, etc., etc., etc. Now, we have to calculate the sound exposure level because of the various sound levels which are measured. You can notice that the sound level is increasing from 64 to 73, 75, 77, and then it is again reducing back as the aircraft goes away. So, what you have to do is you have to just use this formula, and to do that you just have to take the logarithm of all the powers and then you will get the answer. So, I think at this point you should take a picture of this particular screen and you should calculate the noise levels, and then you should compare your answer with the answer which I have obtained. So, take a break here and look at the numbers. The answer is 84 decibels. So, notice that sound pressure level was never recorded more than around 79, but the exposure level, because of the prolonged exposure of various time periods, it is equivalent to having an 84 dB LAE. So, there is something called as the equivalent steady noise level. This is also measured in using a logarithmic equation. So, when the sound pressure varies with time to time, there is something like an equivalent value. So, you have a fluctuating sound pressure level. What is the value of L equal? One single number which corresponds to the average or average disturbance created by the continuous sound pressure level, that is called as LEQ. So, LEQ is measured. Again, we will look at this particular example. There were 4 levels measured for 4 aircraft flyovers. What is the hourly average sound level? So, again the hourly average sound level will be equal to 10 times log of 1 by 3600 for 3600 seconds, summation of all from I equal to 1 to n, 10 into 10 power log ln about 10. So, take a picture of this and try to calculate the number yourself, and then you can compare with the number I got. So, the equation will become like this. There are 4 instances. So, if you take that, finally you will get 58.5 dB, 58.5 decibels. So, notice that the sound exposure levels were very high, but the hourly average comes down because these were 4 instances recorded in 1 hour, and because of the time of 3600, it is the 4 events are divided by 3600, so you get a relatively lower number of 58.5 decibels. Day-night average sound level, LDN. This is the day-night average sound level for 1 day. This is also measured using a logarithmic equation, LDN. And as I said, there is a weight which is created. So, there is a 10 decibel weightage for more than any sound level observed after 10 p.m. to morning 7 a.m. It is called as night time. So, you add 10 decibels weightage. Evening, from 9 o'clock up to 10 o'clock, it will be 0 decibels. So, you can, here there is a two level weightage. During daytime there is no weightage. So, from 7 a.m. to almost 10 p.m. there is no weightage, but after that it will be 10 decibel extra because of the night. So, there are important noise measuring metrics which I will talk about now. So, noise exposure, we have already seen this chart, so we can go ahead. So, there is something called as the composite noise rating or CNR. This is designed to evaluate the land use near the airports and to predict annoyance levels which will happen from the aircraft operations. So, if you look at how SPL can be converted to EPNL. These are very detailed issues which probably we need not really worry about in this introductory course aspect. Okay. Now, this is the formula for the effective perceived noise level, where you have corrections for tones and corrections for the A level sound level. Okay. So, what happens is, when you want to identify how much is the effect at a particular airport because of the noise exposure, we use what is called as the noise contour maps. Each line on this map gives you an equal noise exposure level. The data is measured at different decibel levels, and there is one tool available called as AEDT, NASA's Aviation Environment Design Tool. Using that tool, one can get the annual noise contours, and it dynamically models noise, emissions and fuel consumption, and it is consistent with the ICAO model and the database. Earlier there was one model called as the integrated noise model. The AEDT has replaced that. Okay. So, the noise data plus number of flights plus number of flight tracks, all this gives you the noise contour. So, you can see, for example, at London Heathrow Airport, you can see the noise contours. So, on runway 27L, the areas which are marked under yellow are the noise contour, 85 dBA noise contours by Boeing 787-8 aircraft, and Boeing 787-9 has slightly larger contour, and 767-300ER has a much larger noise contour for the 85 dB. So, this shows us that the noise impact because of 787 is the least among all these three aircraft. Here is another graph of the noise contours over Heathrow, two runways of Heathrow which are parallel to each other. The red lines correspond to noise levels which are above 72 dB, and then you have the green lines correspond to 57 dB. So, you can see that there is concentrated noise at some locations, and the larger areas are covered with 55 dB. Noise levels above 55 dB are not considered to be a problem for the community. Then what we do is we look at the airport, mark the runways, and then we can create the noise pollution map. Again, these are various lines of various dB levels. Okay, so, the 70 is at the center and the outermost is 53 dB. Here is another example of Frankfurt Airport. Now, aircraft are going to approach from various routes. So, all these routes are going to affect the community. So, this is the Frankfurt Airport. This is Luxembourg Airport. Here you can see that most aircraft come and go in only one direction, and therefore, the noise contours are spread like a banana on one length. Quantifying aircraft noise is very important. First of all, we have to follow a balanced approach. We have to look at the reduction of the noise at source. We have to look at the land use planning and management, so that aircraft are operated and people are not allowed to settle down in areas where the noise is going to be much larger. We have to look at the noise abatement procedures, such as the one shown on the left hand side, where you are looking at the noise abatement procedure. Okay. So, you can see, for example, that in the normal takeoff, the aircraft leaves the runway, climbs to a height of 1000 feet. At this point, we reduce the thrust so that the noise can be reduced, and you fly at 1000 feet altitude. This is the normal takeoff. But if you are following noise abatement procedure, you will be forced to fly at a higher altitude and then level out, so that the noise level produced on the ground is lower. Okay. So, you can see that when the aircraft noise reaching the ground reduces by 3/4 when it gains double the height. So, in this case, the heights are actually 3 times. So, there will be much higher reduction in the noise on the ground. The FAA has given the following 4 steps in reducing the environmental pollution. So, we can see the first aspect is the reduction in the aviation noise and air quality, the second sustainability, third is land use planning, and the fourth is enhanced analytical abilities. Here is an idea about how much noise is created by aircraft which are operating today. Okay. So, we have data for these 8 aircraft. The first column indicates the takeoff weight, the typical takeoff weight. This is measured in tons. Then you have lateral, flyover and approach. These are 3 points. I will talk about it in more detail, and you can see the noise levels which are nearly about 89 to 95 in lateral. And the last aircraft, Airbus A350, the data that you are seeing here is little bit preliminary. Okay. So, noise level per aircraft weight, as you can see, as the aircraft become heavier and heavier, the value of the noise level per aircraft weight is going to reduce. Okay. So, heavier aircraft are having the lower value of this parameter. Now, let us look at how the law is at work in creating the noise regulations. The acceptable level is EPNL dB, 80 dB. Okay. 80 dB EPNL is acceptable level, and FAR 36 is the regulatory chapter from the USA, and stage 1 was announced in it came in force in December 1969. So, right from 1970s, people are being concerned about the noise levels. So, for engines with bypass ratio more than 2, stage 2 came in 1985. This was restricted to aircraft which were having max takeoff weight more than 75,000 pounds. Then we had stage 3 regulations in the year 2000. So, 31st December was the last date. Now, the airlines were given a waiver of 4 years if it was found that 85% of the fleet complies with this, and new aircraft have been ordered to come up with the lower noise level. So, there was a concession given. Then, as far as ICAO is concerned, there is an Annex 16 which lists the noise level regulations, and the British regulation, it is BCAR section N. Okay. Now, this is what I was saying, noise measuring points. There are 3 points at which noise ground measurements are made. The first point is called as the approach point, which is 2000 meters or 2 kilometers before the touchdown point. This is important during landing. So, a location which is 2 kilometers away from the touchdown point along the center line of the runway is the location where the approach noise is measured. Then you have a sideline point, the point at which or any line which is 450 meters away from the center line. At that point, how much noise is created at the start of the takeoff, that is called as sideline noise. And then you have a takeoff point, which is a point which is 6.5 kilometers ahead of the starting point. That is the point where the takeoff noise is measured. So, when you report the noise by any aircraft, you report these 3 values. So, these graphs indicate the values of the takeoff noise, the landing noise and the sideline noise for various aircraft. We are noticing that slowly and slowly the graphs are becoming horizontal. That means, we are not increasing or we are not permitting, because there are limits. So, some aircraft are above the limits, so they became redundant. For example, the Boeing 707 was made obsolete because of the regulations, because its noise level was more than what was permitted. Okay. And you can see that the limits are slowly reducing. So, there is a stage 2 limit, there is a stage 3 limit, and these limits are going to continuously come down and down. So, these are the stage 2 noise limits. An aircraft is allowed to operate only if it meets these requirements. Depending on the aircraft weight, you are allowed a particular noise level in takeoff and in the sideline and approach. There are many techniques used by designers to reduce the noise which is produced by the aircraft and especially its engines. Okay. We will quickly have a look at some of these approaches. There are many innovations. For example, if you reduce the number of wheels, you find that the landings are quieter. Okay, that is one way, because when you release the landing gear for coming into land, when you deploy the flaps, when you deploy the slats, these are the ones that create a lot of noise. So many corrective measures are done, there are computer based analysis done, there are wind tunnel testing done, and after that some amount of improvements can be obtained. So there are also some barrier walls which are put up at the boundary of the aerodrome to deflect the noise and to contain the noise within the airport, so that the people do not. This is an example of New Delhi on the bottom, where you can see that the noise levels are going to cut down. So as per the study from IIT Delhi, these barriers are going to cut the sound level by about 16 to 18 decibel, A-weighted level. Okay. This is a 1 kilometer long and maximum 3.5 meter high sound barrier along the boundary wall. Then you also have a preferential runway system, or PRS. Okay. So a runway is used at a particular time of the day and day of the week when certain conditions are met, so that the noise levels are distributed. So you can say that depending on location of the population living near the airport, and depending on the weather conditions, depending on how we can distribute, you can see there are preferential runways which are used. Okay. So these kind of operations are monitored, and then accordingly the routes are decided. Then there are some technologies for reducing the noise. One of the most important way of reducing the turbofan engine noise is to increase the bypass ratio. Bypass ratio is the ratio of how much air is passed through the outside duct without combustion to the total one. So when you increase the bypass ratio, the nacelle diameter increases and the jet noise exhaust is going to reduce. Another way of reducing the noise is to optimize the shape of the engine duct. We can also use acoustic liners in the engine to absorb the noise. These are internal wall liners which dampen the noise. And then you have chevron nozzles, very popular and very famous. You reduce the jet blast noise by controlling the exhaust airflow. Okay. So you can see over the years how because of all these technological initiatives, various engines on various aircraft, they have led to cumulative reduction in the EP and dB over the years. Okay. This is an example of the chevron nozzle on the Rolls-Royce Trent 1000 mounted on the Boeing 787. These were developed jointly by Boeing, GE and NASA. The pressure of airflow through the combustion chamber is more than that of the bypassed air. Okay. So if you have high pressure air and bypassed air together, you can get a loud shock wave. So what we do by putting these chevrons on the back of the outer skin of the nozzle is to enhance the mixing of the exhaust air, and that leads to noise reduction. So sometimes you can see double chevrons. You can see chevrons on the outer nacelle and also on the inner nacelles. All of these are attempts. So you can see here is a picture from a study which shows the turbulent kinetic energy distribution. You can see on the top it is without chevron nozzle. Definitely you can see much higher values of the turbulent kinetic energy. On the bottom you have the same parameter with the chevron nozzles. You can see that there is a larger dissipation and therefore lesser noise. Now there are also other concepts for reducing the engine noise. One way is to use ultra high bypass ratio gear turboprops. This gives you lower noise because of lower fan tip speeds. Then there are gear turbofans. There are open rotor or prop fan engines. These are giving you acoustic reinforcements and that reduces the noise level. Or you can use what is called as intercooled recuperative cycle. So here is an example of a ultra high bypass ratio Rolls-Royce Ultra fan, which has got a very large frontal area compared to the jet. It is a geared turboprop. The bypass ratio is 15:1 and you expect the noise to drop by about 15 decibels. Okay. Then this is an example of a geared turbofan. So, in a normal turbofan, you have constraints on the low pressure fan speed, okay, and in a gear turbofan you couple them through a gear and there can be a improvement in the noise levels. Then this is an example of a prop fan or an open rotor where you have the propeller mounted behind the engine and it is outside, it is not encased inside a cowling. And then this is the example of an intercooled recuperative cycle in which you have got these small heat exchangers. So, you get higher cycle efficiency using the heat exchangers. There is an intercooler which cools the air between the compression stages through those blue colored devices, and then there is a recuperator which recovers the waste heat from exhaust and uses it to produce the thrust. It will then preheat the compressed air that will reduce the fuel consumption. So, the heat from the exhaust is recovered and sent to the compressor so that the air can get heated and it can get compressed. There are also many other concepts. For example, NASA has come up with many technologies. There is active aeroelastic wing where you can change the shape of the wing to reduce the noise. Then you have compliant trailing edges, and then you can also have low noise during landing gear deflection. Here is an example of an active aeroelastic wing where there are no conventional flaps are deflected using hinges and actuators, but here the actuators are already inside and you have an adaptive trailing edge which is adaptively deformed. It is a highly flexible wing which leads to a lot of weight reduction. About 20% weight can be reduced from the structural weight. The actuators inside are going to change the shape as per the flight condition. This is another example of an active compliant trailing edge or ACTE, where you do away with deflectors like flaps. You can see here, this is the flex foil and there is a Gulfstream test bed where it was tested out. So, it is a very unique patented technology. Then NASA has a lot of experiments in the aerodynamics of landing gear and how to reduce the noise, etc. There are also many operational changes for pollution reduction. For example, there is one way normally an aircraft goes into what is called as the normal profile, which is shown in the blue color, where you are supposed to climb at one angle and then level for some time and then again climb, but you can have a continuous climb and a continuous descent. This will reduce the fuel consumption. 500,000 tons of CO2 per year can be reduced, noise level also can be reduced, but the extent of how much CDA can be incorporated depends on the air traffic. So, these are many of the ways to reduce noise so that our life becomes more comfortable. Thanks for your attention. The aerospace engineers are continuously trying to reduce the emissions, the noise and other effects of air pollution onto the atmosphere, and therefore, the air transportation is going to become better and better as we go in the future. Even though the number of operations will increase, the amount of pollution that will be created will hopefully not be that detrimental. Thank you.